Okay, good. So yeah, I got my PhD from Arizona State, and now an assistant professor in Michigan State University. Yeah, I think Dr. Huan Liu already mentioned that I got my PhD from ASU, but he didn't mention that actually we have worked on feature selection for at least 5 generations. So the first generation definitely is Dr. Huan Liu. He worked with feature selection in 1990-something, when I was a kid. Okay, and then I think the second generation is Lei Yu. He is a professor in University of Binghamton, and I think he got a feature selection proposal funded, and then he found the next generation. Then he graduated, and the third generation is Alan. I think he was a software engineering in Google. And he also got a feature selection proposal funded. And the next generation is me, and he graduated. Okay, I was the 4th generation, and I also get a feature selection proposal funded. And also I find my next generation, Jundong, and I graduated. So actually from this story, because we are working on feature selection, actually the most important features to graduate from our lab, if you are working on feature selection, is you get a feature selection proposal funded, and also you find your next generation. I think this is a very long way for Jundong. Okay, good luck. Okay, so I will introduce the conventional feature selection, because when I was working for feature selection, I think it's just a bridge between, we just started to work with the advanced feature selection algorithms. So I witnessed how feature selection evolves from conventional feature selection to those advanced feature selection. So I'm the right guy to introduce conventional feature selection. Okay, when we say conventional feature selection, I think Dr. Huan Liu just mentioned what is feature selection, and I believe everybody should know what is feature selection. So here I only need to explain what does conventional mean. From a data perspective, so when we say conventional feature selection, actually those algorithms work with this data. And in supervised scenario, we will also have labels. So basically in this setting, we only have the data instances, and we have the features, and we present the data in a conventional attribute way. Basically, we assume data instances follow IID, features follow IID. We don't consider any structures or dependencies among data instances and features. And when we consider the structures among the features, and Jundong will next section, we will introduce feature selection with structured features. And when we consider dependence among the instances, and Jundong will introduce basically the linked feature selection and also heterogeneous feature selection. And when we consider the dynamics of features and the instances, we will have streaming feature selection. So basically, the meat part of the tutorial will be covered by Jundong later on. So don't leave. Conventional feature selection has been studied for decades. So there are so many existing algorithms. So we need a very good way to organize them. So if we introduce those algorithms one by one, I don't think we can finish it until the end of the KDD. So we really need a good way. Actually, in the introduction part, we introduced the 2 ways to organize feature selection. So one is from the data perspective. We have supervised one, semi-supervised one, and unsupervised one. From the selection strategy, we have the filter, wrapper, and also we have the embedded algorithms. Yes, we should follow the traditional way. But when we developed our feature selection package, the package also will be covered by Jundong. So we just knew the most important parts for Jundong, okay? So we found that actually many feature selection algorithms that share common techniques. Okay, so when we organize those algorithms from the technical perspective, we get a lot of convenience. Okay, so I will mention when I introduce each group of algorithms. So from the technical perspective, we mainly have 4 groups of algorithms. One is the similarity-based methods, one is the information theoretical-based methods, sparse learning-based, statistical-based, and also other methods. So when we say other methods, basically the probability based on new techniques just studied, or the strongly rely on those 4 groups of methods. So we will mainly cover those 4 groups of algorithms, but we also will briefly introduce what's new and what else, okay? So in the following talk, I will introduce each group with details. I will introduce what's the underlying assumption for each group, and what's the common technique they use. And also, I will use different examples to illustrate, okay? So first, we introduce the similarity-based method. Okay, I think we first look at this example, okay? So in the original data, we have 2 groups of instances, okay? When we say group, basically they are similar within the group, okay? So from the original data, if they are similar, we use the same shape. For example, here they are similar, and here they are similar. And then we use individual features, and then we calculate the similarity. We choose feature 1, and we can get the similarity here. If they are similar, we use different colors to denote their similarities. If they are similar, basically they have the same color, otherwise they are different. Okay? So we choose 2 features. One is F1, one is F2. So which feature we should choose? Yes, definitely group 1. Why? Yes, so basically, data instances in the original space, if they're similar, after feature selection, we also maintain their similarity. So this is the underlying idea of similarity-based methods. So basically, we try to preserve data similarity. So from this perspective, how can we evaluate whether the feature is good or not? Actually, it's like, so a good feature should assign similar values to instances that are close to each other in the original space. So that's the underlying assumption for similarity-based methods. Okay, so the most important concept in similarity-based methods is the similarity matrix. So basically, we try to calculate the similarity in the original space. So there are many ways we can do this. Actually, in some cases, this similarity matrix is explicit. For example, in network data, we explicitly have the similarity matrix, right? But in many cases, we don't have. So there are many ways we can build the matrix. For example, if we can use some kernel functions. For example, here is a RBF kernel. So we can get the similarity, the pairwise similarities between instances. And also, when the label is available, we also can build the similarity matrix, okay? After we get the similarity matrix, and then we need to, how we select the features. So basically, the underlying assumption we have is we try to preserve data similarity. So here, for each feature, we can define a utility function. So basically, the utility function will give a score to indicate how much similarity this feature preserved. Okay, so we try to select a subset of features which can maximally preserve the data similarity. Okay, so eventually we will have this objective function for similarity-based methods. Okay, so this F is a transformation. We probably do some transformations for the original features or for the original similarity matrix. Okay, so you will wonder why. In this way, we can preserve the similarity as much as possible by maximize this objective function. Okay, actually for this term, we can decompose it into, if there are n instances, we can decompose this term into n squared term. Okay, for each term is the feature value of the ith instance, jth instance, and the similarity between I and j. So basically, if the feature values, the distribution of the feature values can be consistent with the similarity between those two instances, we can achieve the maximum, right? And also, here, this is from the similarity perspective. So if we, from the distance perspective, basically, we try to, so here we is a maximal problem. We also can be a minimization problem to minimize the distance between similar instances, right? And actually, when we introduce the individual algorithms, we will, some algorithms will use the distance as the metric instead of the similarity. The only difference is one is maximal, one is minimal, okay? So once we have the objective function, how to optimize it? Typically, there are two strategies. So one is the gradient method. So basically, for each time, we select the features one by one. For each time, we select the one which can maximally preserve the data similarity. This is the gradient one. The second strategy is we can simultaneously select a subgroup of features which can maximally preserve the data similarity. Okay? And so we can say, actually, from this technical perspective, okay, we have the common form of the optimization problem, and we have the common strategies for the optimization method. The only way so that's the one advantage from the technical perspective. Basically, when we know the general form, we know the form for a group of methods. We don't need to care about the objective function. We don't need to care about the optimization method because they share the same one. The only thing we care is how can we distinguish different algorithms in this group. So actually, for similarity-based methods, the way is actually how for different algorithms that provide different ways to transfer the original feature vector and the similarity matrix. Okay? So next, I will introduce some examples. Okay? The first one is Laplacian score. So basically, the Laplacian score is an unsupervised feature selection. The idea of Laplacian score is we try to preserve the data similarity, but also we want the feature have the higher feature variance. Okay? So in this formulation, we can say L is the Laplacian matrix. Here, basically, here is the distance between features. When we select one feature, here is the distance between two instances. So that's why here we try to maximize this score. This is the distance, and this is the variance. Okay? And after several derivations, we can rewrite this form in this way. So basically, as I said, so in this group of methods, we can maximize the similarity. We also can minimize the distance. For Laplacian score, we minimize the distance. Okay, so when we write it in this way, we can say this part is the similarity we try to preserve. Okay, so we can say actually the Laplacian score is a special case of this group of methods. Okay, Laplacian score tries to minimize the distance, and also we will introduce one algorithm which will maximize the similarity. Okay, it's about spectral feature selection. So how many of you know spectral analysis? That's good. Okay, so actually for spectral analysis, we know the eigenvectors will preserve the affiliation matrix information of data instances. Okay, for example, if the data have k-near affiliations, so we choose the largest k+1 eigenvectors. You know, the largest the corresponding eigenvector is a trivial vector because all values are the same. So we need to choose the top k+1. The eigenvectors corresponding to the top k+1 eigenvalues. Okay, and then we combine those k+1 eigenvectors together. We can clearly observe the k blocks. Okay, for each block corresponds to one affiliation. So basically, the idea is the eigenvectors of the similarity matrix preserve the similarity information, right? So how can we evaluate the features? So basically, if the feature value is consistent with those eigenvectors, that means those features preserve the original similarity information, right? So the key idea here is we try to calculate the similarity between the eigenvectors of the similarity matrix and the original feature. So if they are similar, that means the feature preserve the affiliation information, right? So the objective function for spectral feature selection is we consider the top eigenvectors, and then we use the eigenvalue to indicate the importance. And here is the score to indicate how much similarity we preserve. Okay, eventually we can prove we can write it in this way. Clearly, spectral feature selection is a special case of the general objective function. Okay, so what's the common pattern, the common characteristic of Laplacian score and spectral feature selection? So basically, to try to maximally preserve the similarity. Okay, let's go back to this case. If we have a larger feature F3, okay, we also can clearly with the feature F3 can clearly separate the data. For example, we still can find those two group of features, but the distances between those two groups are larger. So which one we prefer when we do feature selection, F1 or F3? Yes. Why? Because so if the distances, the margin between those two groups is small, the risk to misclassify them or miscluster them is still high. This is just like the idea behind SVM. We always try to maximize the margin between different groups, right? So as we introduced the Laplacian score and spectral clustering, they just try to preserve the similarity, but don't consider to pull instance from different classes far away. Okay, so the feature score will consider both. On the one hand, it will preserve the similarity of 4 instances in the same class. On the other hand, it will push instances from different classes far away. Okay? To do this, we define 2 matrices. One is the within class similarity. Okay? One is the between class similarity or distance. Okay? So we defined those 2 matrices in this way. We can see there are some relations between those 2 matrices. Actually, if we use a matrix with all value 1 over n, n is the number of instances in the data, okay? And then we can say the matrix SW is equal to the matrix with all instances 1 over n minus SB, right? Actually, we can find a relation between the within matrix and the between matrix. Because later on, when we derive the formulations, we will use this relation. Okay, the feature score, basically a good feature which can maximize the the distance between different classes, and at the same time, it will maximize minimize the distances for instances within class. So for this score, we have 2 parts. One is the distances for instances between classes. One is within class. Okay. So LB and LA are the Laplacian matrices defined based on SB and SW. Okay. So we can say for feature score, in one hand, we push similar instances similar. And on the one hand, we also put away dissimilar instances. Okay? After some derivations, we can find a relation between feature score and the Laplacian score. Okay? And we introduced the Laplacian score, spectral feature selection, and feature score. So one common characteristic of those 3 algorithms is they use the strategy 1 to select the features. The select features 1 by 1. For each time, we try to select the one feature which can maximally preserve the data similarity. Okay? However, because of this gradient strategy, so the selected subset together the performance may be suboptimal. So can we select those subsets simultaneously? And here is the algorithm trace ratio. Trace ratio will select a subset of features simultaneously, which can maximally preserve data similarity. The definition is very similar to feature score, but instead of select feature 1 by 1, actually it will select the k features simultaneously. Okay. After still we can equivalent this formulation to the general form in this way. Okay. So I will just ignore the details, and as mentioned, we have the survey paper. We have the detailed derivations about how relate this score to the general form. Okay. Yes. So his question is basically your question is how can we reduce the redundancy features, right? Yes, we will cover for next method. Okay, information theory. So yeah, go ahead.
The slide says that it's simple and easy to calculate, but actually if you have a lot of training samples, calculating similarity matrix is not that easy.
Yes, I think I think for algorithms in this group, the most time-consuming part is to calculate the similarity matrix. Yeah, absolutely, you're right. Okay, but fortunately, as Dr. Liu just mentioned, for feature selection, the data is typically wide. Basically, we have a large number of features, but we have small number of instances, right? So even the complexity is n-squared because of the small number of n is in many situations is acceptable. Okay, this is the first one. The second one, actually, recently I published one paper, actually which provide an approximation way to calculate the similarity matrix. Is very fast. Okay. Okay. So I still, because you already found some problems about similarity-based metrics, and also I want to emphasize some advantages. Okay? So first, so once we get the similarity matrix, it's very simple to calculate the feature scores. It's very efficient. Okay? The second one is because most of algorithms in this group are filtering algorithms. That means they don't depend on any specific learning algorithm. So they are very general. Okay? So of course, so you just mentioned, for similarity methods, we cannot handle feature redundancy and also the high complexity to calculate the similarity matrix. Okay? Basically, this is the one disadvantage. You have a question?
How do you compute similarity matrix from the original high-dimensional data? Because does the computation itself suffers because of dimensionality? Everything is very sparse.
Mm-hmm. Yes. So actually, we only give two examples how to calculate the similarity matrix. For example, if in the supervised case, we only need to calculate whether they share the same label or not. We don't involve the original feature space. Actually, we use some Kähler function to estimate the similarity. Basically, we don't need to really access the original feature space. Okay.
If you calculate something like the Laplacian score,
Mm-hmm.
it's a continuous variable. Where would you do your cutoff? Like, what's the rule in order to cut off to saying this is a better feature? These set of features are better features than those sets. Because as a continuous variable, isn't there incremental information gain somewhere?
Yes. Next one, we will introduce the information theoretical based method also.
Again, how would you do this similarity?
Sorry, can you repeat your question again?
How would you do this in a similarity-based method?
You mean for the...
Like, where is it cut off? I mean, if you have a continuous variable, what is an important feature? So I have now my similarity score.
Mm-hmm.
It's great.
Mm-hmm.
Which one do I choose? Do I only choose the top one, top two, top three?
Okay. I think in the end of the slides, we will mention this question is an open question. So basically, now we don't know the optimal number of features we should choose. Okay, it's still an open question, an open challenge. Okay? Okay, good. So we go to the information theoretical based methods. I really like this group of methods. So when I was a student, this is the most painful part because there's so many algorithms in this group, and also they use seems different techniques. But after we introduce, from the technical perspective, you will say, wow, they're so easy. Okay, so we help you save a lot of time. When I was a student, I really spent a lot of time to learn the information theoretical based methods. Okay, and just wait. How can we make it easy for you? Okay, so when we select features one by one, so what's the criteria for us to select features? The optimal criteria. So here, okay, definitely the first feature, we should select the most relevant one. right? And then when we select the common features, we will consider the redundant. We will select the weakly relevant one, but not redundant. Okay, and then we will say weakly relevant one, redundant, and then we just select, so we don't need to select here, this part, okay? So basically, the most, so because this part is redundant, so although the features are relevant, but we cannot introduce extra information by selecting those features. So we should focus on this part. We should select the most strong, the strongest relevant one, and we also want to select the weakly relevant, but they are not redundant. In both cases, we will introduce extra information by adding this selected feature, right? So the next question is, how can we find these optimal features, okay? Before that, I would like to introduce some basis about information theory. Okay, the first one definitely is entropy, but entropy is for some discrete variable x, and the definition I think most of you should know. And in different applications, we have different interpretations about entropy. For example, the entropy can delay the uncertainty in the data, right? And also in information field, entropy means how much bits we need to code this data. So in any cases, if the data follows some patterns, it's not the random case. We should have an entropy less than 1. For example, if we flip a coin, the entropy is 1, right? Okay, so basically the entropy can delay the uncertainty in the data, okay? So we also want to introduce the conditional entropy. So basically in many cases, we need some evidence about about x, so we provide an evidence y, okay? So with the evidence y, can we get more information, or can we reduce the uncertainty of x, okay? We introduce the conditional entropy, okay? So in this case, if x, y are totally independent, so that means the conditional probability of this is pxi, this is pxi, and this part is equal to 1. So we can say the conditional entropy will reduce to the entropy of x if y and x are totally independent, right? So here, if we compare the entropy of x and the conditional entropy, we can say when we introduce an extra evidence y, what we can gain from y. So basically, I just mentioned if y and x are totally independent, we can get nothing. So basically, how can we evaluate what we gain by introducing an extra evidence to x? So we use the information gain between x and y. So basically, information gain is the distance between those two entropy. Okay? So if x, y are totally independent, so actually we can get nothing. This value is 0, right? Okay. And also follow the similar definition of conditional entropy. We provide an extra evidence z. Can we get more? So those 4 basic concepts and the definitions. Okay, we will use them in the following algorithms. So when we search, the basic idea is we try to search the optimal set of features. So one is the strongly relevant. The second group is weakly relevant, but non-redundant. How can we search? Actually, there are 2 search strategies. One is we first select all, and for each time we eliminate 1. Okay, so this is the backward. So basically, the backward search strategy. Okay, another one is for each time, and the initial set is empty, and then for each time we add 1. So this is the forward search strategy. And in the forward search strategy, so what's the criteria we can use to judge whether we should select this feature? There are possible 3 types. So one is we try to maximize the relevance. So basically, how relevant this feature to labels. Oh, by the way, for information theoretical based methods, most of them are supervised feature selection. Okay, we have the label information available. So the first criteria could be select the one which is the most relevant to labels. Okay, the second one is since we already selected a set of features, so the new one should be less redundant with existing one. So how can we evaluate? We can use the information gain. So basically, we introduce a new evidence, a piece of new evidence. Can we benefit the data? So can we gain anything? Okay, this is measured redundancy. And also basically here later on we will introduce this is so within some classes we need some correlated features. If they are not fully redundant, they still can be helpful to improve their performance. Okay, so basically there are 3 basic criteria we can use to select our feature. Here is a general framework, right? So the first part, the relevance. The second part is the redundancy with the existing features. Okay? The third part is the redundancy in each class. Give the label whether they can provide extra information. Okay? So this is a general framework, and here G is a function to combine those 2 types of redundancy. Okay, there are many choices of G function. For example, one could be a linear function. Okay, so basically, in this way, for example, we linearly combine those 3 criteria. One, for example, one is maximal, minimal, and maximal. That's why here we introduce elective, because we try to maximize this score, and we basically equivalent to minimize the redundancy. Okay? And of course, the G function can be nonlinear. Okay, you can see very clear, right? So most of algorithms in this group, they define the different ways. For example, even simple, they just choose different beta and lambda, right? As I just mentioned, when I was a student, I was really painful to learn this group of this algorithm. But now, it is very clear, right? The only thing you need to know, we already introduced the 3 types of criteria. And also, now, what you should know, just how to select beta and lambda. Simple, right? Yeah. Okay, so we introduced some special cases of this general framework. The first one is the information gain. So basically here, we select beta equal to beta and lambda to 0. We get the information gain. Simple, right? So in this way, we only consider the relevance between features and the labels. Okay, because we don't consider redundancy. So definitely you will have a question, right? It's not good. We need to include the redundant. Okay, here we only include the redundancy with the existing with the selected features. And here basically we select from the general framework, we just set the lambda equal to 0. We can get this mutual information feature selection. And here this is one of the most famous algorithm in information theoretical method is MR. So basically, we try to minimize the redundancy but maximize the relevance. But the intuition is actually when we include all relevant features, so the redundancy becomes less important, right? Because it can only will increase the complexity of the model, but will not reduce the performance because we already include, all relevant features. So here, how can we define the beta? So originally, we will set the beta as a constant value. But here, it should be related to the number of selected features. With more selected features, this term will become less important. So this is the basic idea of MR. And another one is the conditional informatics features extraction. So basically here, we also consider the correlations of features in one class. So in many cases, actually, the correlation, two correlated features can introduce extra information. So if I, J, and I are totally independent, so this part is 0. So if they are not totally, they will introduce, although they are correlated, but they will introduce extra information. That's why we also need to include this part. So basically, in this case, we set beta lambda equal to 1. Right? You can say one framework covers most of existing information theoretical based methods if they choose the linear combination. And also, we have nonlinear combinations. Okay, one is we choose the maximal operator, minimal operator, and also we want this part. We don't want to include the lective redundancy. Basically, we want this part to be positive. Okay, and also this one. Okay, so similarly, we will also introduce summarize the advantages, and also there are some disadvantages. Advantages is yes, in this case we deal with the redundancy, right? Yeah, and also most of those algorithms are filtering methods, so they are very general for the learning, for the following learning tasks. But the disadvantage is that most of them are supervised one, and also it's hard to work with the continuous data. So we have to do some discretization with the continuous data. Any questions? Okay, go ahead. Actually not. Okay, that's why we introduced this one. For this one, we have theoretical guarantee. Okay? So the third group is sparse learning-based methods. So for similarity-based methods, for information theoretical-based methods, most of them are filtering methods. So basically, we don't, although they are very general, but they are not optimal for any learning algorithm. So there is another way we can use the wrapper. We can use the specific algorithm as the evaluation task to evaluate the selected features. But this method is very slow because for each time we need to run in the learning algorithm. Actually, a trade-off is the embedding methods. So basically, we're embedding feature selection into model construction. So I just in the introduction, Dr. Huan mentioned the decision tree is one embedded feature selection. We embedded the feature selection into decision tree induction because if the feature is irrelevant, so when we split the loads, we will not mention the in any loads. So that's why we can achieve feature selection. Actually, a more popular way for embedding feature selection is based on sparse learning. Okay, for this group of methods, we have several advantages. One is the theoretical guarantee. Okay, and the second one is actually the performance is very promising. Okay, and the third one is actually is very flexible. We can include the feature information about the features, instances, and about the dynamics, whatever. And I think Jundong will cover this part because I think this part is quite important. It's an introduction for the remaining slides because most of the remaining slides will be based on sparse learning-based methods. So pay attention because you can consider this as an introduction to the remaining slides. Okay. So what is the feature sparsity? So basically, in many real-world applications, we typically use the linear model. So in the linear model, for example, this is the binary case. This is the multi-class or multi-regression case. So we introduce a coefficient W, okay? So each element, for example, the ith element of W indicates the importance of this feature when we construct this learning algorithm, right? So basically, the sparsity means in these weight coefficients, there are many zero entities. If there are many zero entities, that means this feature doesn't contribute to the model construction. So that's why we can achieve feature selection through these weight coefficients. So this is for the binary case, and this is for the multi-class or multi-regression case. Okay, and first we focus on the binary case, and here is a general framework for sparse learning-based methods. So the first term, basically, we use a linear model to fit the label. Okay, so we can have multiple choices of a loss function. It can be least squares, hinge, logistic, and so on. Okay, the second term is the regularization term. So this term is very important. This can help us to achieve feature selection, okay, through this regularization. The ideal case for the regularization is we should choose the zero run of a vector, because the zero run of a vector means how many non-zero entities in this vector. For example, in this case, the non-zero entity, the zero run of this vector is 4. So basically, there are only 4 non-zero entities. So this is the ideal case we want, right? Because we can directly set how many features, the maximum number of features we want to select by control the zero run of the vector. Unfortunately, no free lunch, okay? Because of the convenience, but also because in this case, it involves integer programming. So it's typically very hard because it's the long convexity and the integer programming, okay? So we typically, in real case, we will relax this regularization to the L1 norm, okay? So L1 norm, we can achieve sparsity. I will explain later why L1 norm we can achieve sparsity. And also, this is convex. So there are many theoretical guaranteed solutions, okay? So the most popular L1 norm for feature selection is the Lasso formulation. Here we choose the regularization term as L1 norm. So basically, this is the coefficient. So basically, this is the coefficient vector, and we want to make this vector sparse to achieve feature selection. So basically, if there are zeros, basically it will include the information from the corresponding features when we construct this model, right? And this formulation is equivalent. We can remove the regularization term to the constraint. So there is some study, okay, basically for each, because here alpha controls the sparsity, and here the region, the size of the flexible region controls the sparsity. So actually they are equivalent. So for alpha, we can find a t, we can make those two formulations are equivalent. Let me give you an extreme case. For example, when alpha is infinite, okay? So the solution of W is what? If alpha is infinity, positive infinite, we try to minimize this term, the solution is the trivial solution 0, right? So in this case, we can find a region t equal to 0. So basically, this problem is inflexible. So the only solution is 0, right? So actually, we can find a relation between alpha and t, which we can make those two formulations equivalent. So why the L1 norm can achieve sparsity? So here is one. First, look at those two last figures. So first, we look at the flexible region. For L1 norm, we define a square, basically a square. Okay? In this, and for L2 norm, we define this circle. the circle is a flexible region. So basically, we try to find a solution in the flexible region which can minimize this loss function, right? So why L1 norm can achieve the sparsity? Actually, we can say in the square, there are many tips or spike points, right? Fortunately, those tips are on the coordinator. So basically, that means there are many other values are 0. For example, in this case, those two tips, they're in the y-axis, and the x-axis dimension is 0, sparse, right? And for those two tips, they're in x-axis, so the y value are 0. So basically, we can say the values of those tips are sparse. Okay? Because of these tips, when we search the optimal value, it's likely we will first touch those tips instead of touch any point in this circle, right? So it's likely we will get this kind of solution. Basically, that means for the L1 norm, we can achieve sparsity, okay? So when in the multiple classes case, because we already introduced the vector, it's okay. Thank you. So in the multi-class cases, okay, for each class we introduce a vector basically. Okay, this is for the first class label, for the second class label, for the third class label, and each entity will indicate how important of this feature to the first label, how important of this feature to the second label, and so on. Okay, so when we should eliminate this feature, so in the case if this feature is not relevant to anyone, any class labels, we should remove or eliminate this feature. That's why we need the sparse, this row sparsity. So basically, to achieve row sparsity, we use 2-1 norm. So basically, we first get the 2 norm of each row, and then we put 1 norm on the 2 norm of each row. In this case, so if we can achieve the whole thing at 0, right? Any questions so far? We are almost done, okay, for this part. Okay, good. Laterally, for sparse learning methods, I think laterally is designed for supervised learning. How can we, because of the promise and performance, and also a lot of advantages of sparse learning methods, how can we extend sparse learning methods from supervised learning to unsupervised learning, for unsupervised feature selection? There are 2 strategies. The first strategy is because in unsupervised setting, we care about the clustering performance. So basically, we first obtain the clusters, and then we perform feature selection, a 2-stage methods. And also, we can embed feature selection into clustering, 1-stage method. So which one is better? Which one is better? Okay. So personally and practically, the second one is better. Okay, why? Because actually, when we select different features, we can get different clusters. For example, if we only have the feature gender, so we can have female and male, we have 2 groups. But how about if we only have the feature age, we can have senior people, junior people, okay? But those 2, they're very different, right? The cluster structures are very different. That means when we select features, we should consider cluster structure. When we consider cluster structure, we also need to consider what kind of features. So basically, those 2 processes should depend on each other. So the second strategy basically will consider them independent. So that's why the second strategy is better, okay? Because they're highly dependent. I just give the example of we use gender, we have 2 groups, we have age, we have 2 groups, but those two groups are very different, basically. They have very different cluster structure. Okay? So there are many algorithms So either for this one or either for this one. I will introduce two. So one is the multi-cluster feature selection. Basically, this is a two-stage method. First, we get the affiliation vector, or we get the cluster structure. Okay. So as we mentioned before, actually the eigenvector, I mean the spectrum or the eigenvectors of the similarity matrix will maintain the affiliation structure. So in this case, they will use the eigenvectors as the class labels. And with first group, we get those eigenvectors, and then we use a lasso to feed the eigenvector. Consider this as a label. We feed this cluster structure we found. Okay, this is basically the basic idea. Okay, we first perform get the eigenvectors, and then we perform lasso. Basically, we get the pseudo. We can say this as the cluster labels, and then we do traditional supervised feature selection. So the second way is we embed feature selection into the clustering algorithm. So here, basically, this is the spectral clustering. Okay. So here we get basically G is the affiliation indicator matrix, and then the same thing. But in this case, this is a multiple cluster label cluster case. We use two unknown and we embed them together. Okay. So typically, how to solve this problem? They will do an alternating way. First, we get a G. We get the class label, and then we do feature selection. Once we select features, we will do this kind of alternating until convergent to a stable set of features and also a stable the affiliation matrix. Okay. The same thing I will introduce. So the advantage is we can have very good performance, and also the interpretability is very good because we can explain why we make this predictions, because the coefficient value can indicate whether we include this feature or which feature contribute how much to the model construction. So the interpretability is pretty good. But the disadvantages are because they are embedded methods. Basically, it's optimal for the linear model, but not necessary for others, and also because the regularization term, typically we will use one norm or two unknown is non-smooth, although convex. So the optimization problem is computationally expensive. Okay? The final group is a statistical-based method. So basically, we try to use some statistical measures to measure the feature independence. And also, most of them are filtering methods, and you select features individually, so we cannot, avoid the redundancy. And most of them work with the discrete data, and we need to do the quantization for the numerical features. Okay? And also, I will include two simple examples. One is the t-test. T-test is defined for binary classification. Basically, we have two class labels. And the idea of t-test is we try to find a feature which can separate the different classes. And what's the significance to separate? We use basically how far away the mean or the centers of class labels. Use this one, we will define the t-testing score for a feature. Okay, the second group is the chi-square. So basically, the idea is we want to test given what's the dependence between a feature and a class label. Okay, and I will introduce some notations. First, this one is the R is the number of feature values for Fi has. For example, we can choose. For example, for gender, we have male, female. So what's the value? And then say is the number of clusters we have. Okay, so basically UJS. So so basically here the NS and NJ so is the number of instances S, and also the number of instances with the J's value. What does this mean? This value mean this value means the expected number of instances in class X with the value J. So this is the expected numbers. And this is the observed numbers, okay? So basically, so if the observed numbers is the same as the expected one, that means this feature is useless because we don't need any information we can get this value. So this observed number, small and large, both cases are good. Basically, they include extra information beyond the expectation. So that's the basic idea of chi-square, okay? And for statistical methods that are computationally efficient, actually I have many friends who are working on the computation, they are from the biology, and they use the statistical methods a lot because it's very simple, and it's easier for them to understand. And also because most of them are the filtering methods, so the selected features are very general. But we cannot handle the redundancy, and also this group of methods only work for discrete data, and also this also have some effective issue. Okay. As I promised, I also will mention some other types of methods, okay? So basically, they will use other techniques because there are not enough existing work, or they are strongly rely on the four groups of methods, so I just briefly introduce them. One is the construction. So basically, how to evaluate the goodness of feature. So basically, if we can select the features which can reconstruct the original data better. So basically, this feature should be good. So in this group of methods, this is our measurement about the goodness of a feature. And in this way, we can how to get the reconstruction function with the selected features. How can we use a reconstruction function to approximate the original data? They can be linear or non-linear. Another method is very similar to the ensemble method because actually I need to talk more sentences about this method, okay? So until now, when we say performance of feature selection, we always focus on the accuracy, right? The precision, and the recall, and so on. But in many fields, the stable, we don't consider the stability of feature selection. What does the stability of feature selection mean? For example, in the gene case, okay, in the gene microarray data, okay, for the gene case, we try to find some features relevant to a disease, okay? So when we perform algorithm 1, we get the feature 1, most important. And then we apply this algorithm with different initialization, and we get the feature 2, that basically a lot of different genes. So which gene we should trust? Which gene we should rely on? What's the step? So in many cases, in addition to the accuracy, the stability of feature selection is very important. Actually, the hybrid feature selection can solve this case because we combine feature selection results from a variety of methods and of feature selection algorithms, and we use the agreement of them to do the final prediction. Okay? Actually, in our group, actually there is I'm the 4th generation, and Alan is the 3rd generation. Actually, there is a 3.5 generation. Okay? He was working on the feature selection stability. So if you are interested in, and you can find his thesis from my advisor's website, should be right? Yeah. So for this group of method, yes, we can solve the stability issue. Okay? I think that's my part. And the most important part is those 4 parts. And finally, so let's welcome Jundong, or we should have a break, or Jundong. A few minutes, okay. Thank you.